In this video, I'm going to show how to determine the internal resistance of a battery graphically. Now, we are going to use the circuit that we see here, and we see a battery connected to the terminals of a resistor. And this is the resistor. It has a resistance of 10 ohms. And then we have an ammeter which registers the current that passes through this resistor. And then as it is now, the voltmeter is connected across the terminals of the battery. Now we can see that as the switch remains open, there is no current through the circuit. There is no current in the external circuit, and then the voltage of the battery is now a maximum, and that is 12,00 volts. So this first set of points that we can read here is a current of 0,00 against voltage of 12,00 volts. Then when we switch on this circuit, we see that the current increases from 0 to 1,00 amperes, whilst the voltage drops from 12,00 to 10,00 volts. Now, what we are going to do is that immediately we can read a second set of points, which is a current of 1,00 and then a voltage of 10,00 volts. So to get other set of points, we are going to manipulate the current. And how do we manipulate the current? We make this resistor a variable resistance. That is, we vary the resistance, because we know that current and resistors are related. They are inversely related. So if we want to increase the current in this circuit, what we do is to decrease the resistance of the circuit, and then we will see that the current will be increasing. Then we read the corresponding voltage of the circuit. As it is now, the voltage of that we see here is the voltage of the external circuit, because it's connected now across the terminals of this variable resistor. So let's use a slide to change the resistance in order to manipulate the current. So we are going to decrease the resistance by 1 unit, and then each time we read the set of values of current and voltage. Now when I decrease the resistance by 1 unit, I see the current decreases to 0,1,09, and then the voltage decreases to 9.82. So this is our third set of values, and then we take another set of values, that is 1.20 amperes against 9,6 volts. Then another set, 1,33 amperes against 9,33 volts, and then we have 1,5 amperes against 9,0 volts. So we can take another one, and then the last one that we take is when the resistance is 0. Now we decrease this resistance to 0, and then the voltage across this resistance now is 0, because there is no resistance yet. It's 0 resistance, so no voltage. Now at that point we see that there is a maximum current through the circuit, which is 6 amperes against 0 voltage. At this point we say that this circuit is now, or the battery is now short circuited. That means there is no resistance along the path of the current. So the current is free to flow. No work is done in the external circuit. And that is how we have a maximum current. So let us check and then tabulate the results. Our first set of values was when the current, the switch was open, and then when the current was 0,00, and then the voltage was a maximum of 12,00 volt. So that is it. And then we had, when the switch was closed, the current increased to 1,00, and then the voltage decreases to 10,00 volts. Then there are this other set of values until the current now increases to 6,00 when there is no resistance, or there is zero resistance in the external circuit. That is when the battery is short circuited. Then when we graph these results, let us see the type of graph we are going to get. Now this is a straight line graph. That is a graph of voltage on the y axis versus current on the x axis. So we see that it's a decreasing graph, just as our data is saying. That is, as the independent variable, which is the current, because we were changing the current, as the current increases, the voltage decreases. So this is a decreasing graph, and we see the points plotted there. And then what we need to note about this graph is we need to note three things. That is the gradient. What does it mean? The y-intercept, what is it? And then the x-intercept. Now we can make these relations quickly. Now you remember that when the switch was still open and there was no current in the external circuit, the battery was reading, or the voltmeter was reading the maximum voltage that the battery could provide, and that is our EMF. So the y-intercept here is the EMF of the battery with the switch opened, and then the x-intercept, that is when there is no voltage or there is no resistance in the external circuit, there is no voltage in the external circuit. So a maximum current of 6,00 was registered, and then we call that the short circuit current, or the maximum current, or the current when the battery is short circuited. So these are the 2 points that we should take note to understand what they mean: the short circuit current, and then the EMF of the battery. Then another thing is the gradient of this graph. Now you remember that when in Ohm's law we have an increasing graph, a graph that moves from 0 and increases this way with a positive gradient. Now this is not Ohm's law, but this one, with that graph, when we determine the gradient, we get the resistance of the circuit, and that resistance is the external resistance. But when we determine the gradient of this graph, we get what we call the internal resistance of the battery. The internal resistance of the battery. So let's calculate the gradient of this a graph that is change in the y-axis divided by change in the x-axis and see what we are going to get. What we do is we take any 2 points on the graph. Now you can see the first point here is 8 for voltage versus 2 for current, and then the second point that you are going to take is 4 for voltage and then 4 for current. In fact, you can take any 2 points as long as they lie on the line. It doesn't matter, it will give you the same gradient. So let us see the calculations. Now we have the gradient of the graph, which is a change in the y-axis, or the change in voltage divided by change in current, and then we say is the second point of voltage minus the first point of voltage divided by second point of current minus the first point of the current. Then when we substitute, we remember it was a 4 for the second point, and then 8 2 for the first set of points. And then when we calculate, we get -2 as the gradient. And what that means is that our internal resistance of the battery, which is the gradient of the graph, is 2 ohms. Now the graph we have just plotted is in the form y is equal to mx plus c. That's a straight line graph, and we can see that on the y-axis we have voltage, and then on the x-axis we have what? Current. So if we say that our resistance is the gradient, then it means the M corresponds to what? The gradient, which is internal resistance of the circuit, and then our y-intercept corresponds to the EMF of the battery. That is when there's no current in the external circuit. So we can go and then we see how we can apply this in solving questions. Now we solve this question 7.2. A cell has an EMF E and an internal resistance R and is connected to an external circuit. There is a current I in the circuit when the potential difference across the terminals of the battery of the cell is V. Define 7.2.1, define EMF. And then 7, the next one is the graph below shows the variation of voltage with current for the cell. Now we can see voltage on the y-axis against current on the x-axis. Then let's read the questions. 7.2.2, sketch a diagram of the circuit that could have been used to obtain the data used to plot the above graph. So what we do here is we go back and then look at the circuit if they are referring to this circuit. But what we do is to use circuit symbols to represent, to just draw this circuit. And when we show circuit symbols, now we see the resistor like this, the battery like this. Now ammeter is here, and then our voltmeter is connected across the battery, the terminals of the battery, and then this is our variable resistor. So we can draw it, But let's remember that the symbol for ammeter is A with a circle around it, and then the symbol for voltmeter is V with a symbol around it. So we go and then we draw that circuit, and if we do that, this is what we get. We get a circuit of a battery with the switch, and then the ammeter. Then this is a resistor, but this arrow here shows that this resistor can be changed. It can be varied by pushing a slide or by turning a knob like we did in the experiment. So we call it a variable resistor, and then we see the connecting wires, and that is that for this question. The EMF is the maximum energy per coulomb of charge passing through the battery. That is the answer for question 7.2.1. And then let's go and check question 7.2.3. It says use the graph to determine the EMF of the cell. Explain how you obtain your answer. And these 2 marks. So what we say here is that the EMF is the y-intercept of the graph, and that is when we check the graph, we see that the y-intercept is equal to 1.5. So our EMF is 1.5 volts, which is the y-intercept, and that is that. So we say EMF is equal to 1.5, and our reasoning is that the EMF is the y-intercept of the graph. So it is as simple as that. And then the next question there says we should seven point 7.2.4 says we should use the equation V is equal to EMF minus IR together with the graph to determine the physical quantity represented by the gradient of the graph. Clearly indicate your reasoning. You remember that this graph is a straight line, and it agrees with the straight line equation, which is y is equal to ms plus c, with what is here, which is the voltage corresponding to y, and then I, x corresponding to the current. So what we have to do here is that we rearrange this equation so that it will be of the form y is equal to mx plus c. So when we do that, this is what we get. We say we're given V is equal to EMF minus IR. Now we want this to be in the form y is equal to mx plus c, and we know that V is already corresponding to y, but our x is I, so we only have to swap the positions of this term IR with EMF, and then when we do that, we see that V is equal to I, that is negative IR plus EMF. So we see that Y is corresponding to V, and then M is corresponding to the internal resistance, which is the gradient of the VI graph, and then C is corresponding to the EMF, which is the y-intercept of the graph. Then look at the next question. Now calculate the magnitude of the physical quantity represented by the gradient of the graph. So we are to calculate the magnitude of the physical quantity. We remember that the physical quantity represented by the gradient is the internal resistance. So we have to calculate the gradient of this graph. And what we do is, like we did in the experiment, we measure, or we take any 2 points that are on the graph, and then we use them to find the gradient. So here, the first point here is 1.2 for the voltage against 2.5 for the current. And then the second point here is 0.6 for the voltage against 0.75, because this one is between 0.7 and 0.8, so it's 0.75, and then we calculate the gradient of the graph. So we see the gradient represents the internal resistance of the circuit. Okay, that is the previous one. 7.2.4, we have to determine the gradient. We use the gradient formula that says gradient is equal to change in the voltage, which is the y-axis, divided by change in the current, which is the x-axis. And then the points that we read were 0.6 for the voltage, and then that corresponds to 0.75 for the current at that point, and then minus 1.2 for the voltage, and then the corresponding current was 0.25. So when we evaluate this, we get negative 1.2, and what that means is that our internal resistance is equal to 1.2 ohms, because the internal resistance is the gradient of that graph. Now you may ask, why are we not maintaining the negative? Because if you look at the equation in 7.2.4, we say V is equal to negative Ri plus EMF. We see that the gradient is negative in this formula. So here, to get R, we say that negative R is equal to negative 1.2. So positive R is going to be positive 1.2. That is why the negative sign disappears when we are writing the final answer.